Hello and welcome to this lecture on complex integration. In this video, we are going to see about contour integration of type 1. So, in contour integration, the type 1, that function will consist of cos theta and sin theta. The integral over the limit will be of 0 to 2 pi. Of course, totally we have three types. The type 2 will be in the form of integral over minus infinity to plus infinity f of x dx, where f of x will be in the form of p of x divided by q of x, and type 3 will be in the form of minus infinity to plus infinity sine mx divided by any polynomial q of x dx, or integral minus infinity to plus infinity cos mx divided by q of x dx. So these are the three types under contour integration. Now we are going to study about type 1. So if I am getting any of problem in this form, we have to convert all theta terms to z form. So for that, we have to assume that z equal to e power I theta. If z equal to e power I theta, if I differentiate this equation, I will get the value as I into e power I theta. So within this equation, I may get like d is equal to I e power I theta d theta. So then we may substitute e power I theta equal to z, because that is our assumption. So I have substituted I z d theta. So finally we get that expression d theta equal to d z by I z. So I am just equating this d z equal to I z d theta. From this, d theta can be written as d z by I z. Okay, and we have to convert all theta terms. So we have some other formulas for cos and sin. So here cos theta can be written as 1 by 2 z plus 1 by z, and sin theta can be written as 1 by 2y z minus 1 by z. And if it comes with cos square theta or cos 2 theta, generally cos n theta, sin n theta, or cos power anything cube square, as like that, we have some other formulas. So if it is of cos 2 theta, then we have to take only the real part of z square. Sin 2 theta means we have to take the imaginary part of z square, as same in the general. And if it is of cos square theta, we have a formula that 1 plus cos 2 theta by 2, and of course it is the real part of 1 plus z square by 2, and sin square theta can be rewritten as real part of 1 minus z square by 2. So while if I am getting any of functions that will be in the form of theta, we will convert into f of z. Thus theta will be a trigonometric function with respect to trigonometric functions. We will convert into f of z. So finally we convert a whole function into a contour integral over c f of z. Here we assume that curve as a unit circle, mod z equal to 1. We assume everything. We convert the 0 to 2 pi, a limit over the integral over c as mod z equal to 1. And I have given as general steps to compute the contour integral of type 1. First we have to identify the contour. That means we have to identify the contour type, whether it is type 1 or type 2 or type 3. If it is decided type 1, we have to convert all theta terms in the form of z by using the previous conversions. And step 2, after converting this theta trigonometric function terms to z, we have to find the poles. How do you find the poles? By equating the denominator of the f of z. Suppose I am getting that f of z equal to z minus 2, z minus 3 cube or square. I have to equate this denominator to 0 and I will find the poles. Okay, if I equate z minus 3 whole square equal to 0, na, either any one of this factor is to be 0. So it can be 2 and z minus 3 whole square equal to 0, na, z minus 3 equal to 0, z equal to plus 3. So these are the poles. Okay, so on the next, if those poles are simple, then we have to find the residue for that pole. If it is of pole of order 2, 3, then you have to use this formula to find the residue. So what do you mean by simple pole? So suppose our f of z which has z minus 2. Here it is the power is 1. Then we used to say z equal to 2 is a simple pole. If I am getting that f of z equal to 1 by z minus 2 whole cube, then z equal to 2 is a pole of order 3. Then you have to use this formula. Okay, and the next step, at last after finding the residues, we have to use the Cauchy residue theorem, and finally we have to evaluate the integral over the given curve. So let's move for the problem. So here, evaluate the integral using contour integration. So they have given integral 0 to 2 pi d theta and 2 plus cos theta. It is clearly identifies that it is belongs to type 1. Now next what we have to do? We have to convert all trigonometric terms and theta terms to z. Since we have cos theta can be written as 1 by 2 z plus 1 by z, and d theta can be written as dz by iz. So let's start the problem. So how do we convert this? 2 pi d theta. I may write this equation as 1 second, and this can be written as 1 by 2 plus cos theta can be written as 1 by 2 z plus 1 by z, and here it is dz by iz into dz by iz. On the next step, 0 to 2 pi, here I may simplify this term, 2 plus z by, here it is z square, now I may take 2z, and here dz by iz, here it is 1. And the next step, it will be of 0 to 2 pi 1 divided by 2 plus, I may write the step z square plus 1 by 2z, I may multiply z, it can be written like this, and this can be written in the form of 4z plus z square plus 1 divided by 2z into iz. So z get cancelled and dz will be there. On the next step, 0 to 2 pi, I may bring the 2 on the numerator, and here it will be of 4z plus z square plus 1, and there will be the term I. So I may bring the constants. 2 by I will be a constant. So 0 by 2 pi and dz by 4z plus z square plus 1. So of course we have converted all trigonometric functions and theta terms in the form of z. Now let me find the function f of z. I may take the f of z equal to z square plus 4z plus 1. Okay. So what is our next step? We want to find the poles. The step 2 will be finding poles. So how do we find the poles? By equating the denominator part to 0. 4z plus 1 equal to 0. So how do you find the poles here? I may use a quadratic formula. A will be 1, B will be 4 and C will be 1. So we have a formula minus B plus or minus square root of B square minus 4AC by 2A. So if I substitute over here minus 4 plus or minus 16 minus 4 divided by 2 and it becomes minus 4 plus or minus 12 divided by 2 and this can be written as minus 2 plus or minus root 3. Yeah, I may take 2 over this term, 4 3s are 12 and I may take 4 common from this term and I may cancel 2 and 4 and finally we will get that minus 2 plus or minus 3. So I am getting the value z equal to minus 2 plus or minus root 3. So here it may considered as z1 as minus 2 plus root 3 as one pole and the second pole as minus root 3. Okay, so our function f of z is 1 by z square plus 4z plus 1. So now this is factorized into 2. So it can be written as z minus z1, z minus z2. What is the explanation means? Simply z minus of minus 2 plus root 3 into z minus of minus 2 minus root 3. So this can be written like this. So simply I will take 1 by z minus z1 into z minus z2 for simplification purpose. So now we find the poles. Of course, we want to decide whether it is a simple pole or double pole. Double pole means if it is a order of 2. So I'm having a 2 factors with the power 1. So both poles z1 and z2 are simple poles. Then we want to find the residue. So if this pole lies inside the given curve, what is our given curve? Mod z equal to 1. Okay, so after converting the all trigonometric functions to z form, then our curve will be of mod z equal to 1. So we want to check whether these poles lie inside this circle. Mod z equal to 1, it is simply a unit circle. If it lies inside, we will find the residue. If it lies outside, we won't find the residue for it according to Cauchy theorem. Okay, so let me decide z1. I may check for z1. So what will happen? Minus 2 plus root 3. Okay, so of course, what will be the value? Minus 2 plus 1.732. We know that root 3 can be written as 1.732. So it will be minus 0.682. Definitely it will be less than 1. So z1 lies inside C. Then check for the z2. So our equation will be mod z equal to 1 and z2 will be, we have to check for this. What is our z2? It will be of minus 2 minus root 3. So here minus 2 minus 1.732, here it will give the value minus 3.732. Surely it will be greater than 0. So z2 lies outside outside C. So we want to find the residue for Z1 alone. Of course, it is a simple pole, and we have a formula to find the residue. For simple pole, it will be of residue Z equal to A, f of Z equal to limit Z tends to A, then Z minus A, f of Z. Here, A will be Z1. So, if I apply this, limit Z tends to Z1, Z minus Z1, our function f of Z will be in simplified form, it will be like this, and these two will get cancelled. So what will be the next step? Limit Z tends to Z1, 1 by Z minus Z2. So then if I substitute Z as Z1, it will be of Z1 minus Z2. So what is our Z1 and Z2? Z1 will be minus 2 plus root 3, and Z2 will be minus 2 minus root 3. So then Z1 minus Z2, what will be the final value? Minus 2 minus root 3. So it will be of minus 2 plus root 3 plus 2 plus root 3. So 2 will get cancelled. So we will get the 2 root 3. So therefore, the residue at the point Z equal to Z1 will be 1 by 2 root 3. So at last, applying Cauchy residue theorem, and Cauchy residue theorem will be 2 pi I into sum of residues. So here this is the residue. We find the residue for Z1 alone because Z2 lies outside the circle. So we have only one residue, and of course if you see here, before taking f of Z, there is a constant 2 by I. So here integral over C f of Z dz will be equal to, we will multiply the constant here, 2 pi I into 1 by 2 root 3. So I will get cancelled, then 4 pi by 2 root 3, then 2 pi by root 3 will be the final value.